Welcome back. Our paper folding activity produced a lovely U-shaped envelope. Is it a parabola or a deep fake? In this activity, we will use geometry to expose the truth. A parabola models the envelope quite well, but there is a difference between model and theory. Consider a simple chain suspended at both ends. The chain can be modelled by a parabola, but another curve, called a catenary, derived from the Latin term catenaria, which literally translates to chain, may be more applicable. The theoretical answer involves a lot of physics around frictional and gravitational forces acting on each link. The modelling answer may be resolved by simple visual inspection, but the overall answer depends on the purpose. Consider the building located at 20 Fenchurch Street, London. The building is often referred to as the walkie-talkie building due to its shape. The curvature of the building is not parabolic, but a parabola can be used to approximate that curve. Why is this important? Well, at certain times during the day, light reflected from this building focuses on a relatively small area, increasing the light intensity so much that it actually melts car components. So it's somewhat irrelevant whether the curve is parabolic. The fact that it can be approximated as a parabola means it will exhibit some parabolic qualities. In this activity, we are interested in the theoretical outcome. Is our envelope really a parabola or a deep fake? To answer this question, we need to start with a quick review of the necessary conditions for triangle congruency. In the first case, we have 3 sides of the triangle are equal. In the second case, 2 sides are equal and also the included angle. And in the third case, 2 angles are equal and the included side. So let's return to the original diagram. We had a point on the y-axis, a horizontal line, and we formed an envelope by constructing a perpendicular bisector. Now I'm going to draw a line segment that connects our point on the y-axis to the point on the line. The bisector literally cuts the segment into 2 equal pieces. It bisects it. The angle between this segment and the bisector is of course 90 degrees because it's a perpendicular bisector. I could place a point anywhere on the perpendicular bisector and form 2 triangles. For the purposes of this activity, I'm going to choose a point vertically above the point on the line. This dynamic diagram reveals 2 triangles. Are they congruent? If they are, what does that say about these 2 distances? You may want to pause the video or return here once you've answered this question. Start by referencing the point that will define the locus. Call this point P, x, y. The distance between P and the horizontal line can be defined as d1. d1 is equal to y minus -2. The distance between P and the point on the y-axis can be defined as d2. d2 can be calculated using Pythagoras' theorem. Using triangle congruency, we know that D1 is equal to D2. Now we have an equation relating x and y. So we can transpose or solve this equation to make y the subject and graph the result. Let's compare the graph of our quadratic equation with the locus of point P. The locus and our quadratic equation are the same. The definition of a parabola is a set of points on a plane that are equidistant from a fixed point, focus, and a line, directrix. The locus is a parabola, and the parabola is a quadratic equation. The TI-Nspire activity linked to this video requires you to find the corresponding equation for a range of focal points and directrices. You can return to this section of the video to review how to calculate the equation for each combination. That's all for this video. In the next video, we take a deeper look at why this geometry and definitions around this amazing U-shaped curve are so important. In the meantime, be focused and stay curious.